matter that behaves like a wavy superatom. Making them in space is an opportunity to hold a magnifying glass to the quantum world, but only for a brief period of time.
It is incredibly challenging making something ultra cold because there is nothing in the natural world that wants to be ultra cold. Something like this is so rare, so unnatural, so unlikely that you're talking about the coldest spots in the known universe.
The quest for colder temperatures has gone on for over 100 years. Scientists kind of steadily working to get colder and colder temperatures.
And by cold,
We're talking seriously chilling. Nanokel is a billionth of a degree of absolute zero. Picokelvin is now a trillion.
strange and curious things happen when we get atoms to ultra-cold temperatures. But to understand why colder regimes are an exciting playground for scientists, we have to wade into some quantum mechanics.
Quantum mechanics tells us that everything has both a particle and a wave nature to it. And so at normal temperatures, atoms just kind of act like billiard balls. As we cool the gas of atoms, we lower its momentum, and each particle's wave nature starts to become more and more pronounced.
And if you get cold enough,
These wavelengths get so large, these atoms really start to blur together.
And at that point, this strange new state of matter occurs called the Bose-Einstein condensate. Bose is the person that really came up with the breakthrough to show that particles called bosons behave in this collective way. Einstein predicted that this state of matter would exist, but he thought it was at such a ridiculously low temperature that you would never be able to actually observe it.
this was back in the 1920s when quantum mechanics was the new revolution on the scene. They didn't have the technology to wrangle atoms just yet, but eventually,
Understanding quantum mechanics gave us lasers, semiconductors, transistors.
In the 1980s, people discovered ways to actually use lasers to cool atoms to incredibly cold temperatures. Most people's intuition is if you shine a bunch of lasers on something, it makes it hotter.
but by tuning a laser to a particular resonance frequency, scientists can slow down the motion of an atom, which essentially cools it.
Then in the 90s, people started developing these techniques to move those atoms into magnetic traps, and then use this other technique called adaptive cooling to get to still colder temperatures.
Evaporation relies on losing atoms. And you need atoms to go away to get out of a trap and carry energy with them.
After decades of technical progress, teams finally made Bose-Einstein condensates in the lab. They lasted inside a trap for a glorious 15 to 20 seconds.
It was clear that gravity had a big effect on these systems, and it would be interesting to do these types of things in space, even though it was totally crazy to think about that. We're combining them with magnetic fields, and the magnetic fields themselves are changing and perturbing the atoms. So we would like to turn off the fields and just stop the atoms on their own. But of course, in gravity, they just kind of go plop.
And that's why putting a lab in space offers a unique advantage.
You can shut the trap off, and these matter waves remain floating.
We think we can get to a new regime of even colder temperatures for even longer amounts of time. Make really sensitive measurements.
And that's where this engineered quantum mechanics box comes in.
CAL is a multi-user cold atom lab within the International Space Station.
The heart of it is this what's called a science module, and then inside that there's a vacuum chamber. There's a computer to control everything and to store the data. There's electronics to drive magnetic field coils, and then there's a whole suite of lasers. We have two species that we're trying to trap with rubidium and potassium.
The reason we like to cool those is because they've got one electron in their outer shell. You want to be able to continually drive excited state, ground state, ground state while you cool these atoms.
So we have this little small vacuum that has this little atom chip on top of it, and then that's mounted inside an assembly that steers all our laser beams.